Unit 9, Molecular Geometry, pages 228 to 234, Hybridization. Covalent bonding. Covalent bonds are formed when electrons are shared in a bond. Atomic orbitals must overlap in space in order for the electrons to be shared between the atoms. New orbitals, called molecular orbitals, are formed. Molecular orbitals show the probability of finding electrons around the nuclei in the molecule. Molecular orbitals can be thought of as a mixture of atomic orbitals. The shared electrons occupy the molecular orbitals. So here, in this space of overlap between the two 1s atomic orbitals of these hydrogens, is where the electrons are shared and a covalent bond is formed. And so we say that the molecular orbital looks like this because that is the more probable region of electrons in the H2 molecule. The bond in the picture is made from the overlap of two atomic 1s orbitals. Bonds can also be made from the overlap of s and p orbitals. For example, in the bond between H and Cl, hydrogen is using the electrons in its 1s orbital to bond with the electrons in chlorine's 3p orbital. And so you have a 1s plus the 3p atomic orbitals combined in order to create the molecular orbital. Molecular orbitals, covalent bonds in molecules, are made from two half-filled atomic orbitals. These two atomic orbitals mix together to form a new orbital called a molecular orbital. So here's the 1s of the the 1s of the hydrogen, and then here is the single electron in the chlorine atom in its 3p orbit. And so because these are both single electrons in their orbitals, they can create a bond with one another by overlapping space and creating a molecular orbital. Hybrid molecular orbitals. BeH2. How are the bonds in BeH2 made? Well, here's your beryllium atom, and there is no single electron present. And then in your hydrogen atom, we have the 1s1 electron. Molecular orbitals are made by mixing half-filled atomic orbitals. Beryllium does not have any half-filled atomic orbitals to use in covalent bonding, so it undergoes a process known as hybridization. This is where it's going to take one of its 2s electrons and move it over to the 2p orbital, thus giving it two single electrons, and so now it can create two bonds with these two single electrons, one hydrogen with this electron and another hydrogen with this electron. Hybridization is a process where atomic orbitals are mixed together to make new molecular orbitals. You can imagine that energy is used to move an electron from the 2s over to the 2p atomic orbital. We now have two half-filled atomic orbitals can be used in bonding. The energy used to promote the electron from the 2s up to the 2p is gained back when the bonds are formed. The 2s and 2p atomic orbitals are mixed together to form two new molecular orbitals called sp hybrid orbitals. So here you're going to have your s overlap with the p, one of the 2s, and the 2p. We're going to move an electron from the s over to the p in beryllium. So that's going to be called an sp hybridization when they've become mixed together. And so now beryllium has an s electron and a p electron that they can bond with the two hydrogen atoms. sp2 hybrid orbitals. The molecular orbitals used in making trigonal planar molecules are constructed from one s and two separate p orbitals, and they are called an sp2 hybrid orbital. Such as in the case of boron, where it normally has a 1s2, 2s2, 2p1. However, we're going to move one of the 2s electrons over to an empty p orbit, and now it can create 1, 2, 3 bonds, a 2s and two 2p's. And so we have a 2s and two 2p orbitals, which create three sp2 hybrid orbitals in order to create 3 bonds in boron. Determining the type of hybridization. We're going to write the Lewis structure, then determine its domain geometry, and then look up its hybridization in a table. 2 domains is going to have an sp hybridization, 3 domains sp2, 4 domains sp3, 5 domains sp3d, and 6 domains will be sp3d2. Notice that the number of domains is equal to the number of letters in the hybridization. 1, 2 letters, 2 domains. 1, 2, 3 letters, 3 domains. 1, 2, 3, 4, 4 domains. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. Note the use of electron domain geometry, not molecular geometry, in this table. Example 9.54. What is the hybridization about the central atom in the BH3 and pH3 molecules? Let's draw the Lewis structures. So here the BH3 has 1, 2, 3 domains, and so you can say it has an sp2 hybridization. This has a total of 1, 2, 3, 4 domains, so you can say that it has sp3 hybridization. sp1, p2, p3. sp1, p2. You cannot know the hybridization of a molecule without first finding out its electron domain geometry. Hybridization, and here's your note card, created by shifting electrons from the s to p to create more bonding orbitals. Two bonding orbitals overlapping create a molecular orbital. When you have two domains, you have an sp hybridization, 3 domains sp2, 4 domains is sp3, and 5 domains is sp3d, and 6 domains is sp3d2.